Okay, so let's solve this problem. This is probably going to take a while for me to talk out, but that'll be okay. So we're going to break this basically into two problems. So first, we're going to solve this problem. Let's see. We're going to say this. I'm going to set this equal to 0. We're going to solve this problem. Okay. So we're going to solve this one first. The reason we're solving this one first is because we know u of x0 is 9 sine 3x, and we know u of x1 is equal to 0, and then we also know the two sides are equal to 0. So now, if you think about the x equation, you're going to go from 0 to 0. So the homogeneous boundary value problem is going to be in the x variable. So it's a little more familiar than what we've seen so far. And then it's more familiar. It is a more familiar thing to what we've seen so far than the next part, where it's going to be the boundary value in the y variable. So we want to look at product solution. So u of xy is going to be equal to h of y. H of y, v of x. Plugging in to the PDE gives the following. Okay, so we're going to, when we do the x derivative, we're going to get h of y like this, plus h double prime of y. This is the y derivative. P of x is equal to 0. And this is going to be the equivalent, if we divide both sides by h and by phi, we get the following. Plus, this is going to be equal to 0. Now, if the sum of two things is equal to 0, it means they're just equal to minus of each other. So we're going to have that. And then function of x equals function of y. This must equal to some constant, which we're going to call minus lambda. Now, for the phi equation, the phi equation is going to be, actually let me write it like this. This is the boundary value problem. Phi double prime equals minus lambda phi, and we're going to get the boundary condition. Phi of 0, equals 1, and they're equal to 0. Okay, so we know what this is. So then, we're going to get all these different eigenfunctions. Is equal to sine k pi x. And then the kth eigenvalue is going to be equal to k pi squared for k equals 1, 2, and so on and so forth. Okay, let me sort of run this to make sure it's equal to the same. Okay, so now that's what we have there. It doesn't like that because I'm saying something that's not true. Okay. All right, so now for the h equation, this is h double prime is equal to, okay, we come over here, we've got minus h double prime minus lambda. So this is just h double prime is equal to lambda. So this is h double prime is equal to k squared pi h. So that h of y, okay, this is a second order equation. So this is the first time we've had a second order equation. So h of y is equal to a times e to the k pi t plus b e to the minus k pi t. And since there's a k, I'm just going to put it like this. We're going to see what happens with this in just a minute. Okay. So then the product solution is uk of xy is equal to I did h of t, but that is supposed to be an h of y, like that. Okay, so it's going to be this times the phi. So sine of k pi x. Let's see how that looks. Okay, so now using kind of all of our knowledge about expansions and sine functions and cosine functions and general Sturm-Liouville stuff, in general, the solution to this problem right here is going to be a sum of these guys, and then we do something to figure out what AK and BK are. Okay, but notice that when x is equal to 0, when x equals 0, when y equals 0, when y equals 0, u of x0 is equal to 9 sine 3 pi x. Remember, there's a typo here. I thought I fixed this everywhere, but I keep finding spots where it's not fixed. Sorry about that. This is kind of the annoying thing about using Canvas, is that when I fix something in one spot, well, never mind. This is just the annoying thing about me making these dumb mistakes. But I have to change things everywhere, and sometimes I forget places. Okay, so u of x0 is equal to 9 sine 3 pi x. In other words, if you plug in y is equal to 0 here, you're going to get ak plus bk sine of k pi x. So what this says is that, in principle, we're going to have an infinite series of these sine of k pi x's, but actually, since when y is equal to 0, it's just 9 sine 3x. The only term that's going to be non-zero is going to be when k is equal to 3. So then the solution to this sub-problem, that is just this problem here, not the whole problem, but this problem here, is u of x comma y is equal to, okay, we only want when k is equal to 3 because we have the 3 there. So this is going to be equal to a3 e to the minus 3 pi y plus b3 e to the 3 pi y, y, and then times sine of 3 pi x. Of course, I'm not going to keep writing a sub 3 and b sub 3, so I'm going to write this as a3 and b3, or just a and b. Furthermore, we know that u of x comma 0, well, if you plug in y equals 0 here, this is just a plus b, a plus b times sine 3 pi x. Hence, we know a plus b has to equal 9, because that's what's multiplying it. A plus b is equal to 9. So a plus b is equal to 9. Okay, so let's see how that looks. Okay, so now we need another equation. So I've got two unknowns, a and b. I need to somehow find another equation to relate those to each other, and that's going to be the top equation. That's going to be the top condition, that u of x1 is equal to 0. Also, let me just do it like this. U of x comma 1 is equal to 0. Actually, let me do it like this. 0 is equal to u of x1. Okay, if I take u of xy and plug in y is equal to 1, this is, I'm just going to take this. This is going to be a, y is 1, y is 1. Now, the only way this can be equal to 0 for all x going from 0 to 1 is going to be if that is equal to 0. Hence, a times e, well, this is equal to 0. Okay, So now I've got two equations. A plus b is equal to 9, and a times this is equal to that. Okay, so now there's a number of ways that we can go at this point. I think for now what I'm going to do is I'm going to look at this equation here, and I'm going to multiply it by e to the 3 pi. So then a, okay, when I multiply this by e to the 3 pi, it becomes e to the 6 pi. So then a is equal to b times, is equal to minus b, because you're going to subtract, times e to the 6 pi. Okay, so if we take that and plug it into a plus b is equal to 9, so then minus b e to the 6 pi, whoops, oh, gosh, come on, dude, plus b is equal to 9. Okay, so now we can now factor out a b. Actually, let me write it like this. So then 9 is equal to this. Let me factor out the b here. So it's going to be b, and it's going to be 1 minus e to the 6 pi. This is so annoying that I keep like pushing the wrong buttons. Okay, and so now b is going to be 9 over that. Okay, so u of xy, and again, this is just solving this problem right here. So the u of xy is going to be equal to this, but we know that where do we get our expression for a? A is equal to this, so we're going to write it like this. So a is equal to minus b, so we're going to factor out a b here. Okay, and now it's going to be minus e to the minus 3 pi y times 6 pi. So what we're going to get is minus e to the 6 pi minus 3 pi y, and then plus e to the 3 pi y times sine of 3 pi x. Okay, but now over here, what is b equal to? I solved this for b. B is equal to 9 over that. Let's do this on 2 lines here. Okay, I'm going to copy and paste this. Boom, boom. B is equal divided by this. Okay. Okay, so that's what we have there. Now, if we want to, we can make this a little more symmetric. So notice what happens if I factor out an e to the 3 pi from both terms. So I'm going to have this. So I'm going to have e to the 3 pi. So if I see what's going to happen, I'm going to have this. This is going to be e to the 3 pi. And now I factored out a 3 pi here. So it's going to be minus 3 pi like that. Okay, so let me see how that looks. Okay. Now I can continue. So I'm just going to copy and paste, do a little copy and paste work here. So I've got a 3 pi in each term. So if I want, I can factor out a 3 pi, and it's going to be 1 minus y. So there's a 3 pi in each term. So when you factor the 3 pi out, it's going to be 1 minus y. So I'm going to get rid of this right here. And I'm going to have something similar over here. I've got a 3 pi in each term. So when I factor that out, it's going to be 3 pi. Let's say I have a minus 3 pi in each term, and then it's going to be 1 minus y here as well. Okay, so let's see how that looks. Okay, so let me make sure I did this right. So 3 pi minus 3 pi y, yep. I'm going to have a 3 pi y, yep, and a minus 3 pi. Okay, so now this looks a little more symmetric. And I can continue. So really, this is just to make things look a little bit nicer, completely optional. And by the way, a lot of people ask in the forums about coming up with hyperbolic cosines and hyperbolic sines. That's exactly right. That's essentially what we're doing now. We're sort of converting it into having sort of a hyperbolic cosine, hyperbolic sine, but I'm not going to write those. You look up what hyperbolic sine and what hyperbolic cosine are, and you'll see how you can really express that in those ways. Okay, so now I've got an e to the 3 pi here. There's a couple of things that I can do here. I want, so if I divide the bottom here by e to the 3 pi, which is the same as multiplying in the top by e to the 3 pi, what's going to happen? Well, I don't need these parentheses anymore, do I? I guess I never really needed them. I'm going to get e to the minus 3 pi here, and then this is going to be 3 pi. So let me run this and make sure it looks right. Okay, divide 1 by e to the 3 pi, e to the minus 3 pi. I get e to the 3 pi like this. That looks right. And then now what I'm going to do is I'm going to reorder this. So I've got a minus sign there and a plus sign. I don't really like having minus plus. I'd rather just have it as a subtraction. So let's see. I'm going to get rid of this like that. Do a little of this and a little of that. And this is what we get. Now, notice if we wanted to, and I think I might actually, well, we sort of have some symmetry here. It's like e to the minus 3 pi 1 minus y, e to the 3 pi 1 minus y, over e to the minus 3 pi, 3 pi. And so, here, it's, there's a 3 pi times 1. So instead of having a 1, we have a 1 minus y. So these are all, very similar to each other. In fact, these are both hyperbolic sines. Or hyperbolic sine would be divided by 2, but we can write this as a ratio of hyperbolic sine. We could write this as hyperbolic sine of 3 pi 1 minus y over hyperbolic sine of 3 pi. But I'm just going to leave it like this. Okay, so that is a solution to this problem right here. So that's like the first solution. Now what we're going to do is we're going to solve the second problem. Whoops. But let's just think about what this problem solves first of all. So this problem satisfies the P to E. It satisfies the zero boundary conditions here. It satisfies this boundary condition here, and it satisfies u of 0 y is equal to 0. Okay, but now we're going to look at a similar problem. So we're going to solve the following problem. So now we're going to set this equal to 0, like that. So we're going to solve this. Okay, excuse me. So how do we do this? Well, now let's think about this. So if you look at right here, we know that u of 0 y, when x is equal to 0, we know u of 0 y is equal to 3 sine 5 pi y. We know over here, when x is equal to 1, u of x1 is equal to 0. But we also know along the top and bottom that u is equal to 0. So in other words, the homogeneous boundary value problem is going to be on the y function. So now, now let u of x comma y be equal to h of x phi of y. Now we could say phi of y h of x and then just have, we could say h of y phi of x and then have the boundary value problem on h, but that's just not the typical way we do things. The boundary value problem gets the phi. Okay. And I'm going to just abbreviate this. Okay, so we're going to get frac h of y, minus h of y, minus h of x, h double prime of x. We're just plugging in, separating, solving just as normal. h of x is equal double prime of y, and then this is equal to minus lambda. The boundary conditions for y are phi of 0 equals phi of 1, that's equal to 0, so that phi k of y is equal to sine k pi y. Actually, I'm not even going to do that as an end line. Okay, so we're going to have this and lambda k equals k pi squared. Okay, so it's just another boundary value problem. It's the same boundary value problem we've been solving, except y is our variable instead of x is the variable. So there's nothing new. It's just calling it y instead of x. And so hk of x, this is going to be exactly what we did before, is equal to ak e to the minus k pi x plus bk e to the k pi x. So the product solution is uk of xy is equal to this hk. I don't need a parentheses there, do I? It's going to be that times sine k pi y. Okay, now we know, let me just run this really quickly to make sure I haven't made any LaTeX mistakes. So we know u of 0y is 3 sine 5 pi y. So the only term that's going to be non-zero is going to be corresponding to k is equal to 5. Given the condition u of 0 comma y is equal to 3 sine 5 pi y, this gives, so the solution for this second part of the problem, u of xy is equal to, it's going to be this here, but with k is equal to 5. So it's going to be this, and just like before, I'm not going to write the k's there because k is equal to 5. That's equal to 5. That's equal to 5, and we've got that. Okay, the condition, so then, okay, if we plug in x is equal to 0, we get a plus b. If x is equal to 0, this is a plus b, and a plus b is equal to 3. So we get a plus b is equal to 3. At x equals 1, we have u of, at x equals 1, this is equal to 0. So we've got this. So that goes away. That's 1. That's 1 is equal to 0. Hence, this is equal to 0. Okay, now I'm going to do basically exactly like I did before. So then a is equal to, if I multiply both sides of this equation by e to the 5 pi, I'm going to get a is equal to minus b e to the 10 pi. So let's just go through like I had something very similar. It's going to be very similar to what I did for the previous problem. It's going to be equal to, we'll start off just by saying it's equal to this. Okay, now I know a is equal to minus b e to the 10 pi. So there's a b in each term. So this is minus e to the 10 pi, and then I'm going to factor out the b here. And then I know a plus one other thing I need to say here. Let me come back. Similar to what I have above, a is equal to that. So if you take this expression for a and plug it into a plus b is equal to 3. So then a is equal, so we're going to have this, that, plus b is equal to 3. And then b is going to be equal to 3 divided by 1 minus e to the 10 pi, like that. Okay, all right. The solution to this, again, subproblem, probably should put a hyphen there. Yeah, okay. Is, okay, so we have this. Okay, I'm just going to replace b with what this says it is. Whoops. So this is b. Okay, let's see how that looks. Okay, good. Now, similar to what I did before, I can factor out. If I factor out an e to the 5 pi. Wait. So that something's not. That says pi. What should that say? That should be a 10 here. That should be a 10 there. So if I factor out an e to the 5 pi, and again, this is just to make it look a little more symmetric. And I hope it's clear what I mean by symmetric here. If it's not, just think about what I'm saying. Okay, so we're going to have a 5 pi there, and now this is going to be e to the 5 pi. I somehow keep doing that. Okay, so let's see how that looks. Okay, I factored out a 5 pi. Now I'm going to combine these in the exponent. So I've got 5 pi minus 5 pi x. So it's going to be 5 pi minus 5 pi x, and that one is going to go away. And then, oh, this is a minus 5 pi, not a 5 pi. That's a minus 5 pi. So it's going to be minus 5 pi minus 5 pi x. So that's going to go away. So it's going to be like this. Okay, so let me. All right, 5 pi x minus, 5 pi minus 5 pi x, 5 pi minus 5 pi x. So minus 5 pi minus 5 pi minus, okay. And now we can do something similar. I'm just going to do this one more time. E to the 5 pi, I can just move this down to the bottom, and this is going to be e to the minus 5 pi, and then this will be reduced down to 5 pi. Oh, and I want to do the switch as well. So I'm going to get rid of this. Whoops. Okay. All right. And again, we can think about this as hyperbolic sine over a hyperbolic sine. Okay, so now this satisfies. This is going to be 0 on the other 3 boundary pieces, and it's going to be equal to 3 sine 5 pi y when x is equal to 0. So then the solution to the whole problem is u of xy is equal to the solution to this first part, which is this, plus the solution to the second part, like that, and that's it. Okay, so notice that both of these, by the method of separation of variables, both of these satisfy the PDE. This solution right here is 0, so this solution is 0 on the sides and the top, okay? And it's equal to whatever the boundary value was on the bottom. It's equal to 9 sine 3 pi x. This right here is equal to 0, like on the top, and then this side over here, and it's equal to 3 sine 5 pi y on the right. Okay, so what is this equal to? This whole function here, what is it equal to on, let's say, the top? Well, this function is equal to 0 on the top. This function is equal to 0 on the top, so its sum is equal to 0 on the top. What about the right boundary? Well, this is equal to 0 on the right boundary, on the right vertical boundary. This is equal to 0 on the right vertical boundary, so its sum is equal to 0 there as well. What about, what is this equal to on the boundary? On the bottom, when y is equal to 0? Well, this is equal to 0 when y is equal to 0. If you just plug in y is equal to 0, you get that. What do you get when you plug in y equals 0 over here? Well, when you plug in y equals 0 over here, you have this over that, but with y equals 0, that's equal to 1 times 9. You get 9 sine 3 pi x, which is exactly what it should be. Now, what about on the left vertical boundary? That is when x is equal to 0. Well, if you plug in x equals 0 here, that's 0. What do you get over here? Well, you have sine of 5 pi y, but if x is equal to 0, these 5 pi x terms are gone, and you have e to the minus 5 pi minus e to the 5 pi over the same thing, so that's equal to 1 times 3, you get 3 sine 5 pi y, which is exactly what it should be. So this function here satisfies the p to e and all of the boundary conditions. And the idea is to break it up so that, in general, we break it up into 4 problems, and each problem, the boundary values are going to be 0 on 4 sides, and it's going to be equal to whatever the prescribed boundary value is on that 4th side. Now, for this problem, there's only non-zero on 2 sides, so we only had to do 2 problems. Okay, but in general, we'd have to do 4 problems. Okay, that's it for this problem.